Welcome back. Today we're diving into something called Jordan algebras. Maybe not a household name, but really fascinating. A mathematical structure born out of a crisis, really.
That's right. It came about, well, back in the early days of quantum mechanics, maybe the 1930s. Physicists like Pascual Jordan, von Neumann, Wigner, they hit a snag.
A snag. What was the problem?
Well, you see, in quantum mechanics, things you can measure observables like energy, position, momentum, they're represented mathematically by Hermitian operators. Or matrices, you can think of them like that.
Hermitian operators. Got it.
And you can add them together, no problem. The sum of two observables is still an observable, but the standard way you multiply matrices, adder times dollars, if you do that with two Hermitian operators.
Let me guess. The result isn't always Hermitian.
Exactly. It usually isn't.
Mhm.
So the set of things you could measure wasn't closed under multiplication. You'd multiply two physical things and get something. Well, unphysical mathematically.
Right. That sounds like a pretty fundamental roadblock for building a consistent theory. So how did they fix it?
This is where Pascual Jordan had this quite clever insight. He realized maybe the problem was sticking too rigidly to all the standard rules of algebra.
You mean like associativity, where 8 times B times C is the same as A plus C, that basic rule.
That very one. He proposed a new way to combine observables, the Jordan product. He defined it as 1 circ B frac 1 2 AB plus BA. Basically symmetrize the standard product.
Ah, okay. So you take AB and BDale and just average them.
Precisely. And the beauty is this new product always results in a Hermitian operator if A and B are Hermitian. So, bingo, closure achieved.
Okay, closure solved, but you said it ditches associativity.
Completely. This Jordan product, Waldo circ BA, is commutative. Waldo circ B is the same as Waldo circ A, but it's absolutely non-associative in general. A circ B circ C is usually not the same as Waldo circ B circ C.
So you fix one problem but break a really fundamental rule. Doesn't that cause other issues? Like, how do you even define powers, like L squared or a good cubed, consistently?
Great question. That's crucial, right? For physics, you need powers of observables to make sense. So they needed one more piece, a constraint.
Which was?
The Jordan identity. It's let's just say it's a specific axiom, a rule this new product had to follow. And it's basically the minimal condition needed to ensure the algebra is power associative.
Power associative?
Meaning that even though the full associative law fails, any single element algebra behaves nicely with itself. 1 circ AM plus algebra. Powers are well defined, unambiguous, A22, 3D3, etc. All make sense.
Okay, got it. So a non-associative but power-associative algebra that keeps observables closed. What then? Did they classify these things?
They did. Jordan, von Neumann, and Wigner tackled the classification specifically for what are called formally real Jordan algebras, the ones most relevant to quantum mechanics. And they found, well, a surprisingly limited set of possibilities.
Limited how?
They found these structures fall into two main categories, special and exceptional.
Special and exceptional, what's the difference?
Special Jordan algebras are the ones that, despite being defined with this funny product, can still be thought of as part of a larger standard associative algebra, like symmetric real matrices or Hermitian complex matrices. They fit inside familiar structures.
Okay, so they're sort of tameable. What about the exceptional ones?
That's where it gets really interesting. They found there are families of special ones, but then there's basically only one fundamental type of exceptional, formally real Jordan algebra. Just one.
One. Out of all mathematical possibilities, what is it?
It's called the Albert algebra, named after Abraham Adrian Albert. Mathematically, it's written as 33BO.
333, well, what does that mean?
It means the algebra of $3 times 3 self-adjoint, or Hermitian-like matrices, but where the entries aren't real numbers or complex numbers or even quaternions. They're octonions.
Math that way stands for the octonions.
Octonions, right? Those are the weird number system where multiplication isn't even associative itself, isn't it? Exactly. The non-associativity of the octonion numbers themselves is the deep reason why this algebra, 334 years, which turns out to be 27-dimensional, cannot be embedded into any standard associative algebra. It's fundamentally exceptional because its builder blocks are.
Wow. Okay, so this one weird 27-dimensional structure stands alone. But you hear about it connecting to other really exotic math, right? Like exceptional Lie groups.
Absolutely. It's not just a curiosity, it's kind of a hidden linchpin. The group of symmetries, the automorphisms of the Albert algebra is the exceptional Lie group.
F whole group.
Just from the symmetry.
For this one algebra.
The whole group. And there's more. There's a procedure called the Titz-Kucher-Cantor, or TKK construction. If you apply that to the Albert algebra, you generate another exceptional Lie structure, the Lie algebra E.
So this algebra is sitting right at the heart of some of the most complex known symmetries. F0E?
It really is. It seems to provide the sort of algebraic scaffolding for these highest forms of symmetry, and it doesn't stop there. The weirdness connects to geometry, too.
How does an algebra connect to geometry?
Well, you can look at specific elements in the Albert algebra called projectors, like projections in quantum mechanics. The set of these projectors forms a geometric object, the octonionic projective plane, Math BVOP22.
An octonionic plane.
And because the underlying octonions are non-associative, this plane is the classic example of a non-de Siurguesian geometry. Basically, a fundamental theorem about perspective, de Siur's theorem, fails in this plane. The algebraic exception mirrors a geometric exception.
That's pretty wild. So the failure of associativity echoes through algebra, symmetry, and geometry.
It really ties together. It's remarkable.
Now, we focused on the exceptional one, 323 algebra, but you mentioned the special Jordan algebras too. Do they find uses elsewhere, even if physics mostly moved on?
Oh, definitely. It turns out the Jordan structure, commutative, power, associative pops up naturally anywhere you have symmetry, and quadratic relationships are important, like in population genetics.
I saw it.
The way genes combine from parents, like in simple single locus inheritance. The algebras describing the frequencies of gene types, the gametic and zygotic algebras, they are often special Jordan algebras. The process is symmetric and involves squares, essentially.
Huh. And statistics, too, I think I read.
Yes. Certain aspects of mathematical statistics involving linear models also utilize Jordan algebraic structures. Anywhere that combination rules are symmetric and powers need to be consistent, but strict associativity isn't demanded.
So, recapping the main thread,
Uh-huh.
physicists needed a closed system for quantum observables, sacrificing associativity, but keeping power associativity via the Jordan identity gave them that.
Right.
And classifying these structures led unexpectedly to this unique, exceptional, 27-dimensional thing, the Albert algebra 3-3 Velassen pack,
Built on the non-associative octonions.
which then turns out to be fundamental to exceptional Lie groups like F and Dierroser, and even defines an exotic non-de Siurguesian geometry.
It's this incredibly interconnected picture, all stemming from that initial quantum problem and the willingness to drop one algebraic rule.
It's amazing. And the final thought, even though mainstream quantum mechanics largely set Jordan algebras aside decades ago.
Well, the Albert algebra itself is making a comeback, isn't it? In some really speculative areas of theoretical physics, people are exploring if maybe this unique 27-dimensional structure could somehow be involved in unifying gravity with the standard model of particle physics.
Seriously, after all this time.
It keeps reappearing. So the provocative question for you to think about is, what does it really mean that this seemingly isolated mathematical exception, born from a 1930s physics problem, remains so deeply entangled with the absolute frontiers of symmetry, geometry, and maybe even the fundamental structure of reality itself?
A lot to chew on there. Thanks for that deep dive.
My pleasure.